excited today to share one of our recent work on how to make video understanding much more efficient. So this is work jointly with other folks from Berkeley and NVIDIA. Okay, so to begin with, I first want to talk a little about the background and context about what problem we're trying to solve here and why is this important. So the problem we're trying to solve here is how can we make video understanding, especially understanding videos that are like either super long or high resolution or high FPS to be much more efficient. So apparently video understanding is a very important topic because video is the most important modality that our humans receiving information from the world. And any agent that acts in the real world needs to deal with videos. So it's definitely a very important modality that needs that current multi-modal like big models needs to deal with. And for that reason, we already seen lots of frontier models that are reasonably good at video understanding. For example, like Gemini or like ChatGPT or whatever. So basically what they can do is like just throw in any random video and they can basically describe what happens in the video. And you can also ask a bunch of questions and you can even let it do more complex, for example, like some agentic tasks about the video. So you can see here, like for example, this is a video of some chef cooking some dishes, and if you input this Gemini, it can tell you, like this is a first-person video in a kitchen. The chef is working on like cooking, and it can even list like all the actions that the chef did in the temporal order. So this is great. This means these models can already understand videos to some extent. But is it good enough? I think these video understanding models are probably not as smart as you think. And from lots of aspects, they actually cannot achieve human level capability yet. And one example here is, like as human, when we are looking at this video, it's actually very smooth. It's a very high resolution, very high FPS, and we can basically recognize every single detail, be it spatial detail or temporal detail in the video. But actually, it's not true for these models. So, so deep down there, what the model sees is actually very different from what human sees in the video. So as human, we see like this very smooth, high-res video, but for this model like Gemini, they actually see a very, very low FPS and low resolution video. And this is because they, because of the reason of the efficiency and also the context length, like they cannot really process lots of pixels in a very efficient manner. And this means that they are actually losing lots of information, lots of details from the video. Like they cannot really tell you, cannot really recognize very fine-grained action, for example, in the video. So this is actually not good enough for them to actually work in like different kind of real-world tasks. And apparently, all these frontier models, they realize this is a real problem and it's a really important problem. And they've made different kinds of efforts to try to solve this problem. And one of the game changers is definitely like the super long context length these frontier models have. So this is already a figure that's kind of old, maybe 1 or 2 years ago. But back then, these models already realized it's a problem, and they've already scaled up their context length and trying to like be able to process longer video or high resolution video by that way. So you can see like Gemini I mean, like all other frontiers model now, they can already process like at least 1 million token of context, which is great. But is it good enough? I think to understand videos as well as human do, is probably still far from good enough. So maybe we can do a quick math here. So let's say if I want to achieve human level vision, so in terms of both resolution and FPS. So apparently a human can actually perceive very, very high video resolution and very high FPS. So let's say a human can perceive more, but let's say we use 4K resolution and we use 30 FPS. And then if we count like how many tokens are there in such a video, and even if we limit the duration of the video to 10 seconds, there are still 5 million tokens in this 10-second video, which is like crazy. Like it can just make your context explode very, very quickly. And this is only 10 seconds, not to mention if your agent or if your robot wants to have visual memory that lasts at least minutes or hours or even days, that will be just unimaginable. So this means that even though we have already extended context length very long, it's still not good enough to perceive very long video or very high resolution video with this context length. And this is basically the problem we are trying to solve. We want to make video understanding for long-range video or high resolution, high FPS video to be more token efficient and more compute efficient, such that our video understanding model can be more scalable to like all these like long and high-res videos and be more useful for different downstream tasks. So before we talk about how AutoGaze like tries to solve this problem, we can probably ask ourselves like, how are humans able to process all these videos with so much information there? How can our human process it so efficiently? So it turns out the humans doesn't really need to process all these 5 million tokens because there are actually lots of redundancy in the video, especially for video that have very high resolution and very high FPS. So let's look at an example. So here it's a video of someone drawing something on the paper. So in this video, you can see there are actually lots of redundancy on both temporal dimension and spatial dimension. For example, like on spatial dimension, like although there are lots of pixels in each frame, most of them don't really have very useful information. For example, the background is pure like solid color, so you don't really need to look at every single place in the background. And even in the foreground, there are still lots of redundancy. For example, like there isn't any pattern on the paper, so you can also ignore some pixels from that. And that's basically what human does. Human usually won't really look at places where there isn't much information. We only look at places that have denser information, such that human can like receive more information in a more efficient way. And similarly, on temporal dimension, there's also lots of redundancy because, for example, like in the first few frames, the hand barely moves. So this means that after you look at the first frame, you don't really need to look at the rest of the frames until the last frame where the hand finally moves. So this means that as human or as a model, you can basically ignore most of the information in in the middle frames, and only look at the hands again when it starts to move again. So this is basically how this video understanding for these high-res and high FPS videos is possible, even though they have lots of pixels. And the key here is basically removing all the redundancy in the video, such that the model only needs to process very few tokens to process most of the information in the video. And that's basically what we want to do with AutoGaze. We want to train this model such that it can remove the redundancy in the video automatically for us. And as a result, we can first use the AutoGaze to remove the redundant patches before we feed the patches into a ViT or a MLLM. And then they can be much faster and much more scalable to like long videos or like high res and high FPS. So that's basically what we want to do in this paper. And before I actually talk about how we make AutoGaze, this is just some preview of what AutoGaze can actually do. So you can see that like on the left side is the original video, and on the right side is the like the patches that our AutoGaze can preserve, and what patches that AutoGaze like removes from the video. So you can see that AutoGaze can basically reduce redundancy on both spatial dimension and temporal dimension, as we discussed. So on the spatial dimension, you can see it's basically like removing lots of redundant patches that are not informative. For example, these like background that are solid color, and only preserve the regions that are informative, like the Tom's head here. And on the temporal dimension, you can also see it will basically ignore any object that is static, because you have already seen that in the first frame, and since those are not moving, you don't really need to look at them again. And it will only look at the objects that are actually moving and has new information in every frame. So this, you can see that like basically AutoGaze can automatically remove the redundancy on both dimensions. So how do we actually make this AutoGaze model? So I think this model is basically to build this model, we basically need to design both the architecture and the training algorithm, and also the data, of course. But I think there's one high level like principle that guides us through these designs, which is like what we want the AutoGaze model to do. So what we want the model to do is we basically wanted to remove the patches in a video as much as possible, but at the same time, we don't want it to lose too much information from the video, such that it won't hurt like the video understanding performance in downstream. Okay. So this is basically objective. This is basically a like constraint optimization problem. And in practice, like one thing to notice here that in practice there are lots of ways to measure information loss. And here we choose one way, which is we use like pixel reconstruction loss to measure the information loss. So which means that we want to select a minimal set of patches that are able to reconstruct the original video as much as possible. Because like if you can reconstruct really well, then this means you didn't really lose any information. So this is basically the objective that guides us through like designing the architecture, training algorithm, and also data for the AutoGaze model. And what does the model need to do to achieve this objective? So first of all, the model needs to recognize like which patches are redundant and which patches are not, right? Because that's how it can remove them. So that's obvious. But at the same time, the model also needs to know how many patches are redundant and how many patches are not. Because for different videos, the redundancy level is actually different. Like you can imagine, like for a video that's completely static, every single pixel after the first frame will be redundant. But if it's a video where everything is moving, then there are actually not many pixels that are redundant because every frame has lots of new information. So AutoGaze doesn't only need to know which patches are redundant, but it also needs to know how many patches are redundant, such that it can it's safe for it to not to like remove too many patches or too few patches. So we basically need to design the model and the training algorithm and also the data to basically achieve these two capabilities. And I think for the ease of understanding, I'll probably start with the second to introduce like how we design the model to achieve the second objective. And then we will go back to the first one. So how can we design model and how can we design training such that AutoGaze can recognize which patches are redundant? So first of all, the model design is actually pretty straightforward, I would say, because the only thing we want to do here is we want to input a video to AutoGaze, and it can tell us which patches are informative, right? So how we design this model is we actually design it as a like autoregressive transformer, like basically like a regular LLM, where for a video we can just input the frame one by one, and after each frame, the AutoGaze will autoregressively decode some tokens, where each token will correspond to a path in the input frame. So you can basically think of this as a LLM model, only that the decoded token are not text or words. They are basically patch IDs. And then we just let AutoGaze to decode the patch ID of the informative patches for each frame. And then we input another frame and let it decode again. So basically, in this way, it can process either a static video or a streaming video because it's a causal transformer. So this is basically the model design, which is super straightforward. And then how can we train this model such that it can recognize which patches are informative and which are not? And recall that our objective is to select the patches such that the reconstruction loss is small enough, right? So basically, we can see that the objective here is it's basically minimizing the reconstruction loss for these patches we select. And since the patches are discrete, because the patch IDs are discrete, then it's actually very natural to train this with RL, because RL is the algorithm you want if you want to train something that is not differentiable, right? So it's actually very natural to train with RL, where we can just use the reconstruction loss as a reward, and then we train our model such that it can maximize that actually the minus reconstruction as reward, such that we can maximize that reward, which means the AutoGaze can learn to select the best patches to minimize the reconstruction loss. So what we do here is, for the patches, like from the patches that the AutoGaze select, we basically run a video reconstruction model from the patches to reconstruct the whole video. So here the reconstruction model can be, for example, a VideoMME, or any model that takes in the patches and reconstruct the video. Actually, in this work, we train our own VideoMME, but any video reconstruction model can do the work. And after we reconstruct a video, we can calculate the reconstruction loss for each frame, and then we can use the reconstruction loss as a reward to train RL for the model. So this is actually a very straightforward algorithm to train this model. Although there is one caveat here, which is it's very notoriously known that the RL is actually very hard to train, especially for when you're training from scratch. And here we are not initializing AutoGaze from any model, so it is training from scratch. And we actually found it really, really hard to optimize it with RL in the beginning. So I think in the work, there's one thing we did, which is before we train RL, we actually have another pre-training stage to warm up the model before we can use RL to like fine-tune it, which is similar to how we train LLMs. Like we first do some pre-training stage and then do the post-training stage. So here in the pre-training stage, we actually find a way to collect a bunch of like ground truth gazing data for a bunch of videos. And then we just use this ground truth gazing to supervise the AutoGaze model in the next token prediction way, which is again very similar to LLM. And here I probably don't want to go into too much details here, but here we have this special algorithm to actually obtain these ground truth gazing data, because like there are actually no very large scale ground truth like gazing data set out there, so we need to collect our own. And here we are basically collecting this with like using some greedy search algorithm, which is we just like exhaustively search which is the best hash sequence that can give you the best reconstruction loss for each video. In this way, we can basically get a bunch of ground truth gazing data, and we can use it to supervise. And after this pre-training stage, we find it much easier to fine-tune with the RL. So that's basically the whole training pipeline we have in the paper. So in this way, we can basically train the model to take in a video and then select all the patches that it thinks are important and ignore patches that it thinks are not, which is basically the second objective we discussed. And then let's go back to the first one, which is the AutoGaze like doesn't only need to know how like which patches are important, but it also needs to know how many patches are important. Because if it doesn't know, then the best solution is always to select all the patches, because that will give you the lowest reconstruction loss. So the model needs to know when to stop gazing, such that it can select enough patches to meet some like requirement on the reconstruction loss or the information loss, but at the same time it won't select too many patches for that. So how do we design our model such that it doesn't know, it doesn't only know which patches to gaze at, but also know when to stop gazing for each frame? So if we think about this problem, in order for the model to know when to stop gazing, the model basically needs to know two things. One is the video itself, which is obvious because the video content decides how much redundancy is there. Like as I said, like some videos has lots of redundancy and some have very few redundancies. So the video itself decides how many patches is worth looking at. And then apart from the video itself, there is another thing that model needs to know, which is the requirement on the information loss or the reconstruction loss. Because for different requirements, the model actually can look at different patches. Like if for some task, I really need to recognize all the detail, then my requirement on information is probably very, like the threshold is very low. Then the model needs to look at lots of patches in order to reach that very low threshold. However, if my downstream task doesn't really need to look at lots of details, and it's actually like constrained by the compute or efficiency, then I probably don't want the AutoGaze to look at lots of details, lots of patches. I just want it to be fast. So in that case, I probably can set a very high threshold, such that the AutoGaze can stop very early once it hits that threshold for each frame. So for the model to know when to stop gazing, we also need to have this additional input, which is the requirement of the reconstruction loss. And this requirement can be anything that the user provides at test time. And then given the video input and the user's requirement, how can we design models such that it knows when to stop gazing. So the design we have here is, again, very straightforward, which is when it decodes each patch ID at each step, we also have an additional head, which also let it to decode the reconstruction loss at a step. So this reconstruction loss is basically like how low of a reconstruction loss it can achieve from all the patches that it has gazed up to that point. So for example, here, after it gazed at the first patch, the reconstruction loss will be 1.0 for the first frame. And then after it gets the second patch, it will be like the first two patches together will give you a reconstruction loss of 0.8 for the first frame. And the model will just continue decoding until it finds out that the reconstruction loss at some point is lower than threshold. And then it will just stop there and continue to the next frame. And then it will do the same thing for next frame, which is like for each patch it decodes, it will also predict the reconstruction loss there for the second frame until it falls under the threshold, and then it will stop. And this is basically how the model is designed, such that it can do like this adaptive stopping based on the video content itself and also the reconstruction loss requirement from the user. And combining these two elements, our model can basically, for each video, can know which patches are important and how many patches are important.
So I had a quick question here. So how do the user select reconstruction loss?
Yeah. So here we remember that when we were training, for example, when we were training with RL, we need to do video reconstruction to get the reconstruction loss and training with RL, right? So here, basically what we did is we basically have calculate the reconstruction loss for each patch. Not each patch, but after each patch. For example, we first calculate the reconstruction loss like by reconstructing video from only the first patch. And then we also calculate the reconstruction loss by reconstructing video from the first two patch. So basically, for each patch, we do the same thing, such that we know what is the reconstruction loss we can get after we gaze at the nth patch. And then we can use that reconstruction loss to supervise this head here, such that it can predict the. It won't be super accurate, but it depends on how large your head is, and we don't want it to be very large because we want it to be efficient. But it can predict a reasonably, reasonable reconstruction loss for us.
Okay, cool. So, do you guys have a way to select other than it doing automatically? Can the user look at the reconstructions and select that this is the quality that I want with the efficiency gains, and I was going to the point of do you guys have some sort of a slider or something like that in which the user can select 2 or 3 reconstructions and then check the visual fidelity and the efficiency factor?
Yeah. So we do have this slider where the user can adjust the reconstruction loss requirement. And there is also another slider where the user can basically decide what is the max number of patches it is allowed to gaze for each frame. So I think, yeah, so the user can basically try the reconstruction, try to give it different reconstruction loss requirement, and then see how the video quality is for each result, and then decide what is the best requirement it needs for the downstream task it cares about.
Cool, thanks.
Yep. Yeah, so yeah, that's basically how our model can learn the two capabilities we discussed. And then combining these two, our model can recognize the like informative patches for any like random video. So this is some qualitative results. For example, like the on the left side is the original video, and the middle one is the like the gaze patches from AutoGaze, and on the right side is the reconstruction result. And you can see that for this example, the model is mostly just looking at the moving object, which is the person here. But at the same time, you can see the reconstruction on the background are basically pretty very similar to the original one, although there might be some flickering, which is possibly because the video reconstruction model we train is not good enough. But you can see that most of the information there is preserved. And here's another example which I think is really cool. So you can see this is the person running to the door, and the model is basically looking at this person the whole time. And one thing that's worth noticing is you can see that there's actually a tree that's moving in the background, and the model is actually looking at that as well. So this is expected by design because even though the tree is not very interesting to human, it's like just some boring thing in the background. The model doesn't really know what a task the human wants to do. So it basically will look at every single object that is moving in the scene. So that is by design. So this shows that the model is actually pretty robust at recognizing all the moving objects. But I think there is also something that can be improved here in future work, which is we can probably also tell the model what is the task we care about, or what is the kind of objects we care about, such that the model can ignore the objects that are moving but are not relevant to the current task, for example, the tree. And in that way, the model can probably be even more efficient. But nonetheless, I think it's still a very cool example to show that the model can basically look at all notice all the moving objects here. And here are some results on more out of distribution examples, for example, like cartoons. And this is another example. So you can see that our model is even though our model is only trained on real videos, our model can actually generalize lots of different videos from different domains. And I think this is mostly because our model doesn't really need any semantic understanding. It doesn't really need to recognize, oh, that's Jerry, that's Tom, or there's a table or whatever. Because to recognize which patch is redundant and which are not, all it needs to recognize is these low-level features, for example, like which object is moving and which are not. And I think learning low-level features is actually much more it's much easier to generalize to different domains of videos. Yeah, so that's some quantitative results we have. And to actually verify that our model can actually look at regions that are like informative on spatial and temporal dimension. We did these experiments where, for example, we look at how the gazing is correlated with, for example, optical flow, which measures the motion on the temporal dimension, and also how it's correlated with the detailedness in each patch, which is kind of correlated with the amount of information in each patch. And we see that there is actually a pretty clear correlation between all of these. So this means that AutoGaze can actually look at patches that are informative on temporal or the spatial dimension, which is pretty much expected. Then, so like the hash, like the gazing result looks great, and how can it actually improve the efficiency for video understanding? Because that is our original motivation. So what we did is we try to apply this model to different kinds of videos, including videos with different FPS and different resolution. So you can see here, like the FPS can range from 1 to 30, and the resolution can range from 224 to like near 4K. So one thing we can observe in this figure is obviously when the FPS is higher and when the resolution is higher, the gazing ratio, which is the like percentage of the path the AutoGaze selects in the video, the gazing ratio is lower and lower. And that is pretty expected because for like when the resolution is higher and FPS is higher, there is actually much more redundancy there. For example, like if the image doesn't really have lots of detail and then you just increase the resolution, then the true amount of information doesn't really change that much. So the model should be able to select fewer patches to retain the same amount of information, and in fact it does that. So you can see that like for video that is only 1 FPS and 224 resolution, the gazing ratio is pretty high. It's like 20%. So it means that there is actually not too much redundancy there. But if we increase the resolution to 4K and FPS to 30, which is much closer to what human can see, you can see that AutoGaze can remove most of the patches. In fact, it only retains like 1% of the patches here. And this level of token reduction can actually help us to make our like downstream ViTs and MLLMs to be much more efficient because they can consume much fewer tokens there. So if we measure the latency of our ViT and MLLM, we can see that by using AutoGaze and feeding these ViT and MLLMs with only the hashes that are gazed by the AutoGaze, we can see that latency, or like in general, the efficiency reduces a lot, especially for videos that are high FPS and high resolution, because for low FPS video, there isn't too much redundancy to reduce. So I think the latency of the AutoGaze model itself is kind of dominating in that region. But I think for these super redundant videos, the advantage of AutoGaze is starting to show here. And this is because our model is like designed in a causal way, so it can not only process like static videos, but also streaming videos as well. So we can also like measure the latency on the streaming videos, and we can see a similar trend. And especially this AutoGaze can actually help us to do real-time video understanding on higher resolution or higher FPS. So for example, for ViT, you can see that like if we don't have AutoGaze, which is the blue curve here, then like for 1 FPS and like 1K, over 1K resolution, the model can still do it fine. So the gray region here is where the model can do real time, and white region is where it cannot. And you can see that once we increase the FPS up to like maybe like 10 or 30 FPS, the model cannot really do real time anymore, even for a very low resolution such as maybe 300 or 400. I think for AutoGaze, it can still do real time understanding for 30 FPS and like 500 resolution, or even 1K resolution. So this is actually pretty good improvement. And with these like much higher token efficiency, we can actually make our model more scalable, because if we can use much fewer tokens to represent a video, then this means that with the same context length or with the same token budget, we can actually fit in a lot more video frames. such as videos that are much longer or videos that are high resolution or higher FPS. And by using higher resolution and higher FPS or longer videos, we can actually improve video understanding performance a lot for different video benchmarks here. So you can see that for these regular benchmarks like VideoMME, without AutoGaze, it can only scale up to the point where the FPS is maybe 1 or 2, and the resolution is like 448 or something. And then after beyond that point, it will just explode. But with AutoGaze, it can actually scale up the resolution and FPS to a very high value, and as a result, it can give you better performance than before. And this is this is obvious, especially for the video benchmarks that really need higher resolution or like higher FPS perception. So especially for this benchmark called HLVid, which we also propose in this paper, because we found that all the previous video benchmarks, like more or less, they don't really need very high resolution or very high FPS or very long video understanding. So we propose this benchmark that is focused on both high res and long video understanding, such that we can show fully show the advantage of scalability of our AutoGaze model. So you can see that by scaling the number of frames to 1K and resolution to 4K, the performance boost here is huge. And this is just an example of how our benchmark looks like. So what we did is we basically curated a bunch of videos from YouTube, which are super long, not super long, but like long enough such that current models cannot really handle. And then we look through, and each video is also very high resolution, like maybe 2K or 4K resolution. And then we create a bunch of QA questions where each question really requires paying attention to some very small detail in a single frame, such that the model really needs to look at the whole video and look at every single detail in the video such that it can answer the question. And as a result, we can see this is the performance boost on this benchmark is actually very significant. And this is just some quantitative results, where we can see that by adding AutoGaze to MLLM, which is called NVIDIA 8B, we can actually see lots of the consistent performance gain on all the benchmarks, and on the HLVid benchmark is the gain is very obvious. So yeah, so that's basically how we build our AutoGaze and what our AutoGaze can bring us. And before I jump to the last part, which is where I want to talk a little about our limitation about the model. Is there any question on the previous slides?
Yeah, please feel free to ask any queries here. But I would start by you described the kind of AutoGaze architecture and how the multi-scale patches kind of scale up and down, and the stage 1 of training and the stage 2 of training that you have described in the paper. But would you be covering that here too?
Sorry, you want me to explain more on the training recipe?
Yeah, the training recipe of the stage 1 and stage 2.
Yeah, the training recipe is basically 2-stage. So the first stage is some next term prediction, and second stage is RL. So it's very similar to how LLM is trained. So the first stage, for training, we basically created a bunch of ground truth gazing data, and then we use that to supervise our model. So imagine for each video, you have a ground truth sequence of the best patches it should look at. And then we just supervise this model with this sequence in autoregressive way. And then after this stage, the model can already learn some basic like gazing capability. And then we fine tune it with RL such that it can find better gazing patterns by itself and to like minimize the reconstruction loss even more.
So the first stage that you have is the next token prediction that you pre-train with, and like after that you have the the per autoregressive token that goes through the like the loss prediction, and then you kind of have the post training with RL.
Yeah, that's right. So I think the loss prediction, we have that in both stages. Like in the first stage, when we are collecting the ground truth gazing, we actually also collected the reconstruction loss it achieves after each patch here.
Oh, yes.
So we can use that to supervise the loss prediction. And in the RL stage, when we are doing reconstruction, we also calculate the reconstruction loss for the patches, and we can use that to supervise as well.
Cool. Thanks.
Yep. Okay. So I think lastly, I want to talk a little about the limitation of the current model, and like where we can probably improve in the future. Oh, I see there's another question.
Yeah, better.
Hi, Baifeng. There are still some more questions in the chat. Would you like to take them now, or would you like to take them at the end of the session?
Oh, okay. I can answer them now. Where can I see?
No, like
Okay, so
I didn't find any queries here. Like there are some note takers that have populated the chat.
Yeah, in the Q&A. Yeah, in Q&A.
Okay.
Yeah, in the question and answer section. Yeah. So Shaibu asked the question. Shaibu, would you be willing to ask your question on air? Would you be willing to come on there and ask your question? Shaibu there?
Yeah, hello.
Oh.
Yeah, thank you for the paper. So my question is, how relevant is AutoGaze for small models, like for edge device deployment?
I see. Yeah, that's a good question. So I think like the purpose of AutoGaze is it's basically like to make video understanding more efficient, such that it can fit into smaller devices. So I think this model. So this model is the AutoGaze model itself is really small. It's only 3 million parameters. So it's like much smaller than any ViT or LLM. So it's very easy to fit into any device. And I think with this model, it can reduce the number of tokens by a lot for any device, I'll say. So I think for edge device, it will also allow it to like process like longer or high resolution videos. Although it cannot reduce the number of parameters for your LLM or ViT, so that will still be a problem. You probably need to maybe like distill to a smaller LLM such that it can fit into your edge device. But at least it can reduce the number of tokens in your input by a lot. So that will be a huge boost.
Sure, thank you.
Okay, thank you very much for that question, Shaibu. Reddy Dasari, are you there? Would you be willing to ask your question on air?
Yes, Benedict. Hi, Baifeng.
Yeah, thank you.
Firstly, really a great paper, I must say. It's very useful in security cam systems and video stream understanding. I have 2 questions so far. So the first one is, can we make this feature-oriented rather than more of patch-oriented?
Sorry, could you repeat that?
Can we make this feature-oriented, like image features-oriented over patches?
Oh, I see. Okay, yeah, that's a very good question. So I think We actually designed this to be patch-based instead of feature-based for a good reason. Because what we want to do is we want to reduce, we want to make ViT and MLL faster. So we want to make them both faster. And the only way to make them faster is we need to reduce the number of tokens before we input into any of these models. And since the ViT consumes raw patches, not features, so this is why we want to operate this AutoGaze on raw patches instead of features. But I think for your question, I think training AutoGaze on feature level is definitely feasible and doable. So there might be some, I guess there might be some use cases where you, let's say you probably already have all the features, you don't need to extract them again. So there's no time spent on that. Or maybe somehow you don't really care about how fast it is to extract features, which is possible. And in that case, you can totally like replace the input frames here into some features, and then the patch here, patch ID can also be replaced by maybe the position ID of the feature, and then you do the same training for all the case. Like for example, you can maybe train a feature reconstruction model, and then you can optimize the AutoGaze to select the minimum set of features to reconstruct the original features. So I think that is totally doable. Yeah.
I think for the feature reconstruction, like the use cases, there will be a kind of one-to-one or like the video streaming that we are having in Google Meet. So the facial features, like that will be a very good kind of example of how to use that specifically in the case of compressing and then transferring the features across. So the video stream is kind of compressed there.
I see. Yeah, I think that's reasonable. Yeah.
Mm-hmm.
Great, Mr. Shi. And I also want to ask one more question. So the embedding model used here, is it something like clip, or can you like give more info about it?
You mean the embedding, by embedding model, you mean how we embed the patches into AutoGaze model?
Yes.
Okay. We don't really have any embedding model here because so first of all, we don't really need to use clip because like the task here doesn't really need semantic understanding. It only needs very low level understanding of, like, for example, which object is moving and which object is not. So I think clip is not really necessary here. And actually to keep this whole model to be super lightweight. So like this whole model only has 3 million parameters, which is super small. So we don't actually put any additional embedding. Like there's like a very small like convolutional network that's trained from scratch. It's super lightweight. So maybe we can call that one an embedding model, but that is like just there is no pre-trained weight for that one, and it's super lightweight.
Yeah, thank you so much.
Yeah, thanks.
Hi, Baifeng. Thanks for the amazing presentation. I have one more question.
Yeah.
Yeah, so I see that we are trying to minimize the patches on 2 axes, that is temporal and spatial. And I understand like we are using reconstruction laws, which would lead to getting us best patches to reduce on a spatial axis, but I want more understanding or your thoughts on how this architecture is also reducing patches on a temporal axis, like how we have a global video understanding if we are doing patch by like frame by frame.
Right. Yeah, that's a good question. So I think, so first of all, the objective for reducing temporal redundancy is that we want our model to not to look at any repeated information more than once. For example, in these two frames, after it looks at the hands in the first frame, it doesn't really need to look at them again in the second frame because the hands are not moving and there is no new information there. So I guess in general, we want the model to learn is we want the model to recognize which patches in the subsequent frame is already observed and has the same information in a previous frame, such that it doesn't need to look at them again. So how the model learns that is, you see that here the model is autoregressive causal, right? So let's say that if in the second frame there are some patches that has the repeated information as in the first frame, then what the model can learn is model can actually look at, because model has a full history, it can look at both frames, and it can also look at the patches it selected in the first frame. So remember that here each patch selected will be the patch ID will be input to the model again because it's autoregressive. So the model can actually decide which patches in the first frame, in the second frame, has the same information as the first frame and is already gazed at in the first frame, such that it can learn to not to select them again. So this is on the architecture-wise, this is how the model is able to learn this. And then how the model actually learns this is basically using this RL algorithm, which means that we want to minimize reconstruction, or we want to keep the same reconstruction but with fewer patches. So compared to repeatedly looking at the same patch for different frame, apparently if you only look at the patch once and not them again in the subsequent frames would be a better solution for the RL, because it's basically fewer patches but with the same amount of information required. So this is how the model can actually learn that from the training algorithm we have. And then from the result, you can actually see that. I'm not sure if you can see it clearly, but let me pause it here. You can see that for the first frame, where is it? Yes. So for the first frame, the model actually looks at most patches, because all of these patches are new information for it. But once starting from the second frame, you can see the model will just start to look at only the patches that are moving and ignore the patches that are not, because those patches have the repeated information as the first frame. So it doesn't need to look at them again. Yeah, so
that's really
I'm not sure if
interesting.
that answers your question.
Yeah, definitely. And I think this AutoGaze can be also a model as a pre-task for object tracking, because inherently it is learning it.
I think to do object tracking, you still need some semantic understanding.
Yeah.
Yeah, I think with AutoGaze, it cannot do it really well, because you can imagine a case where two persons are walking towards each other and then they cross their path and go away. Then AutoGaze will look at the patches where the two persons are moving, but it can it cannot really track which patch come from. When the two persons cross their path, it cannot really know which patch after that corresponds to which person before that. So you know what I mean? Yeah.
Got it. And I have one more. Thank you so much. I have one more question on the benchmark slide. If you can go that one. Yeah. So what's the previous one with the 5 plots? What's happening here if we increase the number of tokens? Again, there is a decrease in performance in VideoMME or HLVid benchmark.
Yeah. So what happened here is for a model without AutoGaze, we cannot really scale it up to like lots of frames or high resolution because the tokens will just explode. So for the baseline, it will just stop here. Like for the other point, it will be maybe 100 tokens or something, which it will explode. And since we cannot use lots of frames, as a result, the performance is low because we are losing lots of the information in the frames that we are discarding from the video. But for AutoGaze, we can actually use lots of more frames and high resolution here. So this means we can we can process more information from the video, and the performance is just higher because of that. If that makes sense.
Yeah, but I guess if you see the plot on token number 30 in VideoMME, and then if you increase the number of tokens, again, there is a drop in performance for AutoGaze. And same for the long video bench. You see, if you increase the number of tokens, there is still a drop from token 10 to token 30.
Oh, I see. I see. You mean, I see. You're asking why there's a drop.
Exactly, yeah.
Oh, okay. Yeah. So I think
there's something related to benchmark, or it's just the batch, or?
I think it's because this benchmark doesn't really need very high resolution here. So when you're increasing resolution here, theoretically, the performance shouldn't change because there's no the question doesn't really need to look at very high resolution detail. So the performance should stay the same. But I think the reason why it's dropping a little bit is, I think one is noise. Another is probably because when you are looking at too many frames, the model it's actually harder for the model to learn. So I think one experiment you can run is for text understanding. If you, for example, text retrieval, for example, if you put a correct answer within the 1,000 tokens in the context, but at the same time you increase the context length higher, to longer and longer, and you can see that the model performance will actually drop a little by little, because the model can always see the answer from the recent 1,000 token, so the performance should always be the same. But because the context length is longer, it makes model hard to learn. So maybe there is a little bit drop there. Yeah.
Makes sense. All right. Thank you.
Yeah, thanks. Okay. I'm not sure.
So,
yeah.
I'm sorry. There are still a few more questions.
Okay.
On the slide. So would you like to still keep answering them? We have 3 more questions on the slides here. On the presentation. Yeah. Sorry.
Oh yeah, I only have 2 slides there left. It's mostly about.
Okay.
I can finish them,
okay.
and then I can take more questions.
Okay.
Yeah. Yeah, I think the limitation is actually a fun part, because the model itself is definitely not perfect now, and there are 2 kind of failure cases we see from our experiments. So the first failure case is, what if the video has camera motion? So previously, the video we show here, it's basically the camera is static, but the object is moving in the scene. But what if the object is static and the camera is moving? Then in that case, theoretically, imagine for example, in this video, the scene is the same, but the camera is moving to the left. So theoretically, for each frame, there actually isn't any new information, except for the leftmost column in each frame, because those pixels are the new pixels that's coming into the frame. But for other pixels, you've already seen them in the previous frame, so they are actually not new information. So this means that the best solution here is actually the model should only look at the leftmost column for each frame, and then ignore all the patches on the right. So that's the ideal solution we want the model to learn. But unfortunately, our model is not able to do that right now. So you can see that our model is actually still looking at lots of patches on the right side for each frame, which are technically repeated information compared with previous frame. So this means that our model will actually waste a lot of tokens in this case. So I think this is, there are multiple reasons like why this happens. I think the first of all is our model is probably not very big enough to learn to disentangle camera motion from object motion. So like it's actually a non-trivial problem. Like if you give it a video where the camera and the object are both moving and you want to disentangle them, it's not trivial. And our model is only 3 million parameters, so it's probably not very able to do that. So that is probably one reason. And another reason is probably in data, because in current data, we don't really, we added some data with camera motion, but I think it's probably still not enough. So that is another possible reason. So I think in the future, maybe if the model can be improved, like with respect to this to this problem. Yeah. And another limitation, which is the model doesn't really need to know, or doesn't really know how to reduce redundancy based on some physics common sense. So one example here is like given a video where a ball is just freely falling. So if you know, imagine if your model knows how gravity works, then it can actually predict the trajectory of the ball given the first frame. Right. So this means that if the model can predict it, it basically means it's redundant information. So the model really doesn't really need to look at the ball at every frame because it can predict where it would go. But I think if like in practice, our model cannot really do that. Our model will just look at it all at every frame. So I think the reason here, again, I think there are several reasons. One is the model is not big enough to learn this physics. And another reason is our video reconstruction model is not good enough. You can see that if we only input the first 6 frames into the video reconstruction model and let it to reconstruct the later frames, the model will just predict that the ball will stay at the same position. So the reconstruction model cannot really doesn't really learn this. So there's no reason for our AutoGaze model to learn this. So I think there are some multiple reasons here, but it would be cool if the model can reduce the patches based on some physics common sense. That would be super interesting. But our model cannot really do that right now. Yeah, but I think like with even with these limitations, I think the model can still do a lot for reducing tokens for like high res and high FPS videos. So I think it's still pretty useful. I think there are also lots of like aspects where we can have some improvements on. Yeah. Okay, so that's basically all I want to talk about today. Thanks everyone for coming, and I'm happy to take more questions.
Yeah, thank you very much, Baifeng. So yes, there are still a few more questions. So Cynthia, are you still here? Would you be willing to ask your questions on air? Cynthia, are you there? Okay, I don't think he's here. So I will read out the questions.
Mm-hmm.
So basically he's asking if there is a baseline with random selection of patches, especially for the out of distribution cartoons.
So if there is what?
If there is a baseline measurement with random selection of patches.
Oh, okay, yeah. So they are,
because he says here that especially for the out of distribution cartoons, because he mentions here that in for those cartoons the AutoGaze selection seems to be a little bit chaotic.
That's it. Yeah, I think there there can be some noise in the patch selection here. I think that's expected. And as for the baselines, I think okay, I didn't put it here, but I think in the paper we had some baselines of different methods for token reduction in ViTs or VLMs. I think most of those methods are based on attention scores in the model. For example, they look at which patches in the ViT are getting more attention and which are getting less, and then remove those tokens that are getting less attention in later layers of the ViT or VLM. I think most of them are working like that. And as a comparison, our model can basically reduce the number of tokens before the ViT input, such that the whole ViT and the VLM can enjoy this token efficiency. So I think that is one biggest difference between our model and theirs. Yeah, but I guess on performance-wise, we can also reduce more tokens than theirs. So I think there's a table in the paper that shows that.
Okay, thank you very much. Then there is a question from Michael Smith. Is Michael Smith here? Would you be willing to come on air?
Yes, I am here. Can you see me? Okay, good. Well,
yes.
Thanks for the talk. If I seen this earlier, I would have come by your poster.
Nice.
So my first question is, first of all, can AutoGaze be added to an existing model, against a Quen or something else like that, or does it require the whole end-to-end training of the network? Because that's not quite clear to me.
Yeah, I think we actually tried to adding it training free to existing VLM. I think that will give you some performance drop because the VLM is not really trained on only looking at partial patches for a video. So I think you probably need to have some fine tuning to at least restore the performance of the original model. But I would say the fine-tuning stage that it doesn't need to be full training. It probably needs a small set of data, subset of data to do that. But yeah, you do need some kind of training to make it perform well.
Okay, so you're getting savings at inference time at the cost of a little bit of training and fun times with RL.
Yeah, I mean, I guess hopefully at some point we can use this to train a VLM from scratch, in a native way. I think, or I mean, at least in the future, if we want to train VLM for robotics, for example, we definitely need some kind of token efficiency method, and we need to do that in the beginning of the training, such that the model can fully adapt to this partial observation of the patches. So yeah, I think that would be pretty exciting.
Right. Yeah. Okay. Thanks. And then my second question is, why NVILA as your base model? Why not Quen or Intern or something else? Because I never heard of NVILA until I was looking at your paper now.
Right. Yeah, it's because I was interning at NVIDIA when I was doing this work, and VILA is actually the work from the group I was interning in, and we have the full access of the data, the code, and etc. So that's why we use it.
Okay, I just have no considerations.
Yeah. That's true. Yeah.
All right. Thank you.
Yeah. Thanks.
Okay. Yeah. Good questions. So we have one final question from Preeti. Preeti, are you here? Are you here, Preeti?
I guess not.
She might not be here, so I'll just read out the question.
What?
I will just read it out. I will read out the question. So she's curious about whether AutoGaze can work on tactile videos, videos that are obtained with gel sites and stuff like that. She's curious to know that.
Yeah, that's a very interesting question. Yeah, for gel site video, I feel like the video there doesn't really have like clear boundary of objects and such. It's mostly some like blurb of regions where some regions are red and some regions are black, like different colors represent different different amount of force and direction of force, I think. So, but I think there should be some redundancy there, although it also depends on how high of a resolution your geosite has. I think if it's very high resolution, I think there's still some redundancy here. And also it depends on like how accurate or high resolution of the tactile signal does your downstream task need. Yeah, I can imagine like if you train AutoGaze on that kind of video, you will still have the advantage of, first of all, temporal redundancy reduction, which is if your touch stays the same, the model will ignore basically all the frames after the first frame because the image will be the same. And on the spatial dimension, I guess the most token reduction probably comes from like using like lower resolution patches to represent each frame, because especially if your downstream touch doesn't need very high resolution touch, I think the model can like use fewer tokens for you to effectively reduce the resolution for you. So I think that's on the spatial dimension. So yeah, I think overall, I think it's still possible. I think it can be very interesting to try. I think especially for temporal dimension, it will make sense. Especially like considering that like most of the time, your robot is probably touching nothing. So the whole image is like empty. So the model will reduce lots of redundancy there.
Okay, fair enough. Thank you very much. So that's the last question I can see here. Thank you very much. Okay.
Yeah, thank you. Thanks for inviting me here. Very happy to share.
It's nice having you here.
Yeah.
Thank you very much.
Okay. Y'all have a good day. Oh, is there anything else?
So before you leave, you could just share with the folks where they can find you, where they can discuss further research with you if you are open to doing that. Of course, we would be open to sharing more of your research with our community. So if you would like to present any of your further works with us, you can discuss with myself or with Mayank via email. Can you hear me?
Yeah. I mean,
so,
yeah, definitely. Like if anyone has more questions or want to discuss anything, feel free to email me. I think I have my email on my homepage. So yeah, very happy to keep on discussion.
Okay. Thank you very much, and it's nice having you with us here. So
yeah,
thank you, and bye everyone. We'll meet in our next guest speaker session. So take care and bye. Maya, you have anything to say?
Not right now. I think so. Baifeng, you can join us on Discord. The link that we have sent you. There's this computer vision channel, and we can tag you there, and you can like engage with the community and ask and answer queries if anybody is interested in your research directly there. So that will be a good addition.
I see. Where can I find the Discord link?
I think so.
Oh, okay. I see it. You sent it me to my email, right?
Yeah.
Okay, yeah, I see. Okay, thanks.
If you click there, I think so you will be able to join in.
Let me try it. Yeah, I need to create an account, but yeah, I think I should be able to join.
Okay. There's no issue then. Like, yeah, you can create your account and then join in, and we will be happy to host you there too. Because there's this open community and we have open research problems, and there are other researchers and students and uh, curious minds who continuously like probe and ask queries, and we discuss ideas, and we form project groups, and like we do our projects like uh, through the expedition. I've been involved in 3-4 projects, and like after that, like the period in which I got TPU access from Google, and we like worked on some projects together. So like it will be great to have you there.